Have you ever wondered how computers perform calculations? It all boils down to a fundamental concept: binary addition. Computers use a system of zeros and ones called binary to represent information. Adding these zeros and ones is crucial for performing any arithmetic operation. That's where digital adders come in. These ingenious circuits are designed to add binary numbers efficiently. From the simplest calculator to the most powerful supercomputer, digital adders form the backbone of digital computation. Without digital adders, computers as we know them wouldn't exist. They are essential for everything from basic arithmetic to complex simulations and data processing. In the upcoming sections, we will delve into the fascinating world of digital adders and explore their inner workings. Let's start with the basics: adding single binary digits. Binary digits, or bits, are the fundamental building blocks of all digital systems. They are represented by either a 0 or a 1. Understanding how to add these bits is crucial for grasping more complex digital operations. This is where the half-adder shines. The half-adder is a simple yet powerful digital circuit that performs the addition of two single bits. It is the cornerstone of binary addition and is used extensively in digital electronics. It's a simple circuit with two inputs and two outputs. The inputs are the two binary digits we want to add, and the outputs are the sum and the carryover. This basic operation is essential for understanding how computers perform arithmetic. The inputs represent the two binary digits we want to add, either a 0 or a 1. When we add these bits, we need to consider both the sum and the carryover, which are the two outputs of the half-adder. The outputs provide us with the sum of these digits and a carryover, which is crucial for adding multi-digit binary numbers. The sum is the result of the addition, while the carryover is used when adding the next higher bit. The half-adder achieves this using two fundamental logic gates, XOR and AND. These gates are the building blocks of digital circuits and are used to perform logical operations on binary numbers. The XOR gate produces a 1 output only when one of its inputs is a 1, representing the sum. This means that if both inputs are the same, the output will be 0, but if they are different, the output will be 1. The AND gate produces a 1 output only when both inputs are 1, representing the carryover. This means that the carryover will only be 1 if both bits being added are 1. These simple gates, combined in the half-adder circuit, lay the foundation for more complex addition operations. By understanding how the half-adder works, we can build more sophisticated circuits that perform multi-bit binary addition, which is essential for all digital computing. To understand the half-adder's behavior, we use a truth table. It systematically lists all possible input combinations and their corresponding outputs. This table shows that when both inputs are 0, the sum and carryover are 0. When one input is 1, the sum is 1 and the carryover is 0. Finally, when both inputs are 1, the sum is 0. Remember, 1 plus 1 in binary is 10, and the carryover is 1. This truth table captures the essence of the half-adder's functionality, demonstrating its ability to add single binary digits and generate the correct sum and carryover. While the half-adder is great for adding single bits, it falls short when dealing with multi-bit binary numbers. That's where the full adder comes in. It takes 3 inputs, the 2 binary digits to be added, and a carry-in from a previous addition. This extra input allows the full adder to handle carryovers from previous additions, making it essential for adding multi-bit numbers. Like the half-adder, the full adder produces 2 outputs, the sum of the inputs and a carryout for the next addition. The full adder is slightly more complex than the half-adder, but it builds upon the same principles of logic gates to perform its function. Let's examine the truth table for the full adder to grasp its behavior. The full adder is a fundamental building block in digital electronics, used to perform binary addition. Understanding its truth table is crucial for anyone delving into the world of digital logic design. The truth table for a full adder consists of 3 inputs: input A, input B, and carry-in. These inputs represent the binary digits that are to be added together, along with any carry from a previous addition. The outputs of the full adder are the sum and carryout. The sum is the result of the binary addition, while the carryout indicates whether there is a carry to the next higher bit. Let's look at the possible combinations. When all inputs are 0, the sum and carryout are both 0. For the combination of 0, 0, 0, the outputs are 0 and 0. When input A is 0, input B is 0, and carry in is 1, the sum is 1, and carry out is 0. For the combination of 0, 1, and 1, the sum is 0, and the carry out is 1. When input A is 0, input B is 1, and carry in is 0, the sum is 1, and carry out is 0. For the combination of 0, 1, and 1, the sum is 0, and the carry out is 1. When input A is 1, input B is 0, and carry in is 0, the sum is 1, and carry out is 0. For the combination of 1, 0, and 1, the sum is 0, and the carry out is 1. When input A is 1, input B is 1, and carry in is 0, the sum is 0, and the carry out is 1. For the combination of 1, 1, and 0, the sum is 0, and the carry out is 1. When all inputs are 1, the sum is 1, and the carry out is 1. For the combination of 1, 1, and 1, the sum is 1, and the carry out is 1. This table showcases all possible input combinations and their corresponding outputs. It is a comprehensive representation of how the full adder operates under different conditions. The truth table demonstrates how the full adder considers the carry-in from previous additions to generate the correct sum and carry-out. This is essential for ensuring accurate binary addition. The full adder's ability to handle carryovers makes it a vital component for performing additions on multi-bit binary numbers. This capability forms the basis for more complex arithmetic logic units, or ALUs, within a processor. In summary, understanding the full adder truth table is fundamental for anyone working with digital electronics. It provides insight into how binary addition is performed and how carry operations are managed. Mastering this concept is a stepping stone to designing more advanced digital systems and contributes to the development of efficient and powerful computing devices. Section 6. Half adder versus full adder, spotting the difference. The key difference between a half adder and a full adder lies in their ability to handle carry-ins. This fundamental distinction is crucial for understanding how more complex arithmetic operations are performed in digital electronics. A half adder can only add 2 single-bit binary numbers and generate a carryout. This means it is limited to the simplest form of binary addition, which is sufficient for basic operations, but not for more complex calculations. In contrast, a full adder accepts an additional carry-in, allowing it to be cascaded with other full adders for adding multi-bit numbers. This capability makes full adders indispensable in the construction of arithmetic logic units, ALUs, and other critical components of digital systems. Imagine you're adding the binary numbers 101 and 110. The process involves not just adding the individual bits, but also managing the carryovers that result from each addition step. A half adder could add the first 2 digits, 1 and 1, but wouldn't be able to incorporate the carryover from the previous addition. This limitation makes it unsuitable for multi-bit binary addition, where carryovers are a common occurrence. A series of full adders, however, would effortlessly handle this, propagating the carryovers throughout the addition process. This cascading effect is what enables full adders to perform multi-bit binary addition efficiently and accurately. Therefore, while half adders are suitable for simple single-bit additions, full adders are essential for building more complex arithmetic circuits that can handle the complexities of multi-bit addition. This distinction is not just academic. It has practical implications in the design and functionality of modern digital systems, from simple calculators to advanced computer processors. Section 7. Full adders in action, powering your processor. Full adders are the workhorses of modern processors. They play a critical role in performing the numerous calculations required for everything your computer does. Inside your processor's arithmetic logic unit, or ALU, you'll find an array of full adders working tirelessly to execute instructions. Whether you're browsing the internet, editing a document, or playing a game, full adders are crunching numbers behind the scenes. These tiny circuits are responsible for adding data, calculating addresses, and performing logical operations. Without them, your computer would be unable to process information or execute even the simplest tasks. Section 8. Beyond simple addition, the impact of adders. While we focused on addition, it's important to remember that adders form the building blocks for other arithmetic operations as well. Subtraction, multiplication, and division can all be implemented using a combination of adders and other logic circuits. This versatility highlights the fundamental importance of adders in digital electronics. They are not limited to simple arithmetic, but serve as the foundation for a wide range of computational tasks. From basic calculators to advanced graphics processing units, adders are essential components that enable the digital world we live in. Section 9. Conclusion. Small components, big impact. Half adders and full adders, despite their seemingly simple nature, are critical components that underpin the functionality of modern computers. They are the unsung heroes of the digital age, quietly performing countless additions every second to power our digital world. By understanding the principles behind these fundamental circuits, we gain a deeper appreciation for the ingenuity and complexity that goes into designing and building the technology we rely on every day. From the smallest microcontroller to the most powerful supercomputer, adders are essential building blocks that enable the magic of computing.